Hello. This session is building big data applications using Spark and Hadoop. And I am Maxim Lukyanov, Program Manager on Azure Big Data team. In this session, we'll talk about Spark, one of the latest and greatest projects in open source ecosystem for processing big data. In this session, we'll talk about how Microsoft made this project available on Azure Cloud as part of your tools. We'll start from discussion of Apache Spark. We'll give it a fairly high-level overview, and then switch to a discussion of features more specific to deployment of Azure Spark on Azure Cloud. We'll talk about a variety of connectivity and tooling options that are available in Azure HD Insight Spark that make development and data exploration tasks more productive for data scientists and developers. So, what is Apache Spark? Apache Spark is an open source project that became fairly popular in the last couple of years for processing of big data. It presents a new computation framework that more flexible and generic than computation framework of traditional Hadoop. In Hadoop, MapReduce paradigm that used for big data computation was fairly simple, and that was its advantage in the beginning. But as time goes, that became its liability. And with Apache Spark, Apache Spark offers basically a more flexible framework that now replaces this MapReduce paradigm from Hadoop. But it wouldn't be correct to say that Apache Spark replaces Hadoop as a whole. In fact, Apache Spark lives and uses many components of Hadoop ecosystem and operates and becomes part of it. For example, there is a HDFS file system from Hadoop that Apache Spark integrates with. There are a variety of data formats that Apache Spark uses, and even at the resource level, resource management level, Apache Spark also leverages Yarn resource framework from Hadoop. So there's two projects live together, and this will be a topic of discussion in this talk. One of the great advantages of this more flexible framework of Apache Spark is its ability to unify various workloads within the same computational framework. Not only you can do traditional ETL jobs as part of Apache Spark core, you can also do interactive SQL queries using Spark SQL. You can process real-time stream of real-time events using Spark streaming, and also machine learning libraries and graph processing libraries available for Spark as well. All of those libraries not only integrate with each other, all of these workloads not only integrate with each other, but they also use common computational framework and execution engine, which benefits from the same, which allows all of these workloads to benefit from the same optimizations and improvements. Within Azure, we recently released a preview of Apache Spark, which made this technology easily accessible to Azure Cloud developers. It is available as a fully managed service, which means you can create an Apache Spark with few clicks cluster that is configured with Apache Spark in a few clicks, and Microsoft will provide full support for these clusters that is backed by not only by Microsoft but also by open source company Hortonworks that provides backend for the distribution that we use on HD Insight clusters. To give you a context, let's switch quickly into Azure Dashboard. In Azure, you have access to a variety of services, and one of them is HD Insight clusters. Here you can find a variety of clusters, and if you click Add button, then you'll be able to provision your own cluster in few clicks. Let's specify some name for it. And you can see that you're able to select a cluster type, which could be a Hadoop, HBase, Storm, or Spark. So similar principle of deployment applies not only to Spark, but to rest of the Hadoop projects in the Hadoop ecosystem. Once you select the cluster type, you can specify a variety of configuration options, including one of the most important, number and the type of the nodes that will be used in the cluster. You can select from smallest to the largest compute nodes available in Azure. So we work closely with Hortonworks and open source ecosystem to deliver you latest releases of Spark available at the moment. We also provide SLA that allows you to rely on our support, and also 24/7 on-call team that fixes issues as they arise with your running service. But in addition to delivering the latest and robust bits of Spark, we also offer a variety of enterprise features and integrations for Spark, such as certification with a variety of security standards like ISO 27018, SOC, and HIPAA, and etc. In recent months, we also announced new big data repository, which is Azure Data Lake, that allows big data computational frameworks such as Spark to leverage higher scalable storage with increased limits and performance. Soon, this integration will come to Spark clusters, and that would allow even more higher scale workloads to run on it. And in addition to that, we also offer high availability for all of the services that we run on the Spark. And we'll talk about it in more detail later. Before we go into the next step, we need to discuss some of the configuration options in Spark clusters in Azure. There are multiple workloads that you as a developer can run on a Spark cluster, be it an interactive SQL workload or some ETL job written in Scala or Python. That's the capabilities of Spark, or even a real-time streaming workload. So all of those applications more frequently are run at the same time on the cluster. So in order to facilitate efficient resource management for all of these workloads while they're running on the cluster, we configured Spark clusters to use Yarn as a resource manager. And that allows us to efficiently provide efficient way to manage resources between those applications that are concurrently running on the cluster. There are multiple ways to create these applications, like the traditional way for Spark using command line, using Spark Shell or Spark Submit commands. There is also an ODBC interface pre-configured on the cluster, which you can use to connect Tableau or Power BI tools. As well as there is a new data science-oriented productivity tools in the form of the Jupyter Notebooks. Those can create interactive sessions that also consume resources in Yarn. Those are connected through a job submission Livy server. This is our collaboration with open source community again, where we kind of improved and enhanced this Livy server to support scenarios around notebooks and remote job submission. So across all of these endpoints, resource management across them is managed through Yarn. If you look at the Spark cluster, not only it provides a variety of core services of Spark, it also provides within Azure Cloud, it also provides a variety of integration points and development tools. First, this is done with a goal of focusing on providing most productivity for within the development cycle. Cloud inherently is well suited for big data workloads, especially machine learning workloads of Spark. you can increase your cluster size dynamically, and that effectively will compress the execution time of your job, because you can throw more compute at the problem. So that's that core benefit of the cloud is further supported by productive development tools. And the development tools span range from initial stages of data exploration and experimentation to development and to deployment. So let's start with the initial phase of the data exploration and experimentation. For that, we have developed additional extensions for Jupyter notebooks. So let's switch into our Azure portal and take a look at that. So I selected one of my demo clusters, and on this pane you can see a variety of settings of this cluster. You can see that it's using just 2 nodes of the D14 VMs, and it also provides access to a variety of dashboards. There are system dashboards that are coming from Hadoop, like Yarn Management UI here, and Spark History Server, and the Ambari console available from this link. But there is also a link to a Jupyter notebook pre-installed on the cluster, which is a tool that we designed for data scientist community and for data exploration. So Jupyter is another open source project which was formerly called IPython Notebooks. It's a very popular notebook service server which we integrated with Spark. So within this Jupyter notebook, you can create different types of notebooks. There are PySpark, Python 2, and Spark available at the moment. So PySpark is a notebook that provides Python interface integrated with Spark. Python 2 is a traditional notebook type coming built in with Jupyter, which we intend to remove because it doesn't have native integration with Spark. And Spark type of the notebook is in the Scala notebook integrated with Spark as well. So by clicking on this new button, you can create any type of the notebook. But there is also pre-built samples that you can see with any deployed cluster. For example, if you go into Scala, we will see a variety of tutorials in the form of the notebooks. We can also go into a PySpark, and see even more of different types of notebooks. Let's take a look at this machine learning notebook to see what these notebooks are capable of. So the advantage of notebook is that it combines both text and actual code. So if you look through this notebook, you'll basically have a tutorial of how to do a simple machine learning job with Spark. Each piece of code is formulated as a cell. You can execute the cell directly in the notebook using Shift-Enter gesture, or you can say simply run all cells, which we'll do. And while the notebook is running, we can go through it and look at primary parts of this notebook. So this is a Python notebook, so it uses PySpark interface. The first step you can see here that in the notebook, grab the text file, CSV text file, from the wasb location. Wasb location is a file on the blob storage account associated with this cluster. So once this file is captured in this variable, we can start experimenting with it. So for example, this cell took the first row of this CSV file. So here is a sample of it. And the second cell actually created a data frame and converted it into a tabular representation with known field column types. So now once this is done, we can further play with this data, and now we can use a show command to represent first 5 rows in the tabular format. And we can go even further using data frames, Spark data frames APIs to do select SQL-like queries in a functional language, as well as we can do a direct SQL operations using percentage SQL command, which is called magic in Python notebook, which instructs notebook to execute a SQL command directly. So that would be a Spark SQL command executed over the data frame that we just created from the CSV file. The result of the execution of the SQL query triggers automatic visualization. So that's one of the features that we have built with our integration of Python notebooks with Spark. This piece of integration is called kernel. We call it Spark Magic kernel. And it's an open source project that you can use on any notebook server, not necessarily in Azure. And it allows you to, as a customer, to quickly build visualizations from the results of the SQL queries. That allows you to quickly gain understanding of the data and make next steps in the data exploration. Another powerful magic here, percentage local, allows execution of any Python code directly in the notebook. So that disconnects notebook from the Spark cluster, but allows you to use any of the libraries that you're familiar with in Python. So one of them is matplotlib library, which is a very popular library for data visualization. So if capabilities of automatic data visualization are not sufficient, you can use direct Python code and this library to do more powerful visualizations. In this scenario, it just builds another type of a pie chart that shows results of the that shows different varieties of the inspection results. And moving forward, we can do more of the machine learning functionality, label the data, and then start doing logistic regressions using Python libraries from Spark Python. And finally, we'll arrive at comparison of predicted and of comparison of the machine learning models that we trained here and the test results. So let's take a look at the final chart. Here, again, using matplotlib library, we can say we can compare results of the prediction, whether we had true negatives, true positives, or errors. So you can see that the models, that the simple regression model that we trained on the food inspection results allows us to predict results with a fairly high accuracy. So the error rate, combined error rate here is 12%. So moving back to our slide deck to give you a reminder of where we were. The next type of the data exploration, once you kind of extracted data and shaped it into correct form, is to use BI tools like Power BI or Tableau. So we actually have samples of that integration present in the Jupyter as another notebook. So we can take a look at the notebook that describes how to integrate BI tools with Apache Spark on Azure AGD Insight. In the interest of time, we'll just look through this notebook that basically is a guidelines of how to connect Apache Spark cluster on Azure to Power BI and configures some simple report to retrieve some results, visualizations of the data. And in a similar way, it describes how you can use our ODBC driver for Spark to connect Tableau to the Azure Spark cluster as well. And finally, after the data exploration and experimentation stages are done, you would likely want to start development and move to a more robust forms of the development environment. So given that there are no Scala plugins available for Visual Studio, we decided to implement, our team implemented IntelliJ plugin and basically made IntelliJ directly connectable to Azure. So now we are in the IntelliJ IDE, and we can go into our settings to see how this plugin is available. So in the plugins section, let's zoom in a little bit. In the plugins section, you can type in HD Insight, and our plugin will become available. Given that I already have it installed, I have an uninstall button, but you'll be able to just install it from here directly within the IntelliJ environment and get all of the functionality. So once you have it installed, you can create specialized projects that have HD Insight integration in them for Scala and Java. You can also convert existing Scala or Java projects to enable plugin on them. Our documentation site provides instructions of how to do that. And once you created a project or converted a project to enable the HD Insight tools, you're able to submit jobs directly to Azure HD Insight cluster from your project. For example, here I have a simple Scala program, which you can see here, just constructs Spark configuration, then constructs Spark context, and executes a job. If you look inside of this job, you'll see that it's again captures some input file, does some filtering on it, and saves it as an output. So fairly simple job. So now, in order to submit this job into a cluster, I'll simply click Submit, and in this Spark Submission UI, it will connect to my Azure subscription, and given that I already authenticated myself, it doesn't ask me for password again, and it now shows me a list of clusters available in my subscription. I can select which Spark cluster I would like to submit my job to, and I can specify also resource utilization parameters such as amount of memory to allocate for a driver, amount of memory for executors, and once I have this specified, I can submit it directly from here. If you look closely, you will see that it's automatically builds and uploads jar files from my application into Azure Blob Storage account associated with my cluster, and then submits job using Livy job submission service. Livy in its turn will use Yarn to create Yarn container for our application and start executing the application. Here we can see all of the steps of the process, and now our application is in the running state. And if we switch back to our Yarn manager, we should be able to see our application executing. So let's launch Yarn UI, and now we can see. Okay, let's switch to running applications. Yeah, it's already finished. So let's switch to finished to all applications. You can see that the Livy service just finished successfully execution of the job. Okay, let's switch back and confirm it here that yes, our job has successfully completed. So that's kind of a direct submission of the job to a cluster, which is a convenient mechanism for you to run jobs at scale. But what about debugging of the job, which is the most complicated part of kind of distributed software development? There are two advanced mechanisms that our IntelliJ tools offer. The first debugging mode is local debugging. So here I can open a Scala test and demonstrate how local debugging looks like. So in this mode, in Scala test, we have this test that describes the purpose of the test, within which you can see that I call Spark sample execute job the same method that I execute from the main method, but with the different parameters. Now, instead of specifying files located on the blob storage account, I specify small test datasets located locally on my local machine. And again, in the Spark configuration, I directly specify the Spark master to use local mode. So in this mode, Spark will run my job fully on my local machine and won't use resources of the cluster. And that would allow me, for example, to set breakpoints inside of my job and debug my job as it executes the code. So that's most productive way to kind of find initial set of bugs in your job. But what happens when your job works on the small test dataset but fails on the large dataset in production? So there is also advanced mode of debugging that we support, where you connect to the remote cluster and basically do remote debugging. This is achieved through a VPN connection to a cluster virtual network. So let me start this VPN connection. So what this does is in Azure HD Insight clusters, including Spark clusters, support provisioning into Azure virtual networks. And you can connect your development machine directly to the Azure virtual network, in which case your local machine attains full network visibility into all of the nodes in this virtual network in Azure, which is a requirement for a more advanced form of the remote debugging to work. So now that I have connected my local machine to the remote cluster, I can demonstrate the third mode of the development in IntelliJ, which is remote debugging mode. In this case, we will directly set the master into a Yarn client mode, which means that when this job runs, it will detect the Yarn cluster, remote Yarn cluster, and will submit job to it using the cluster resources. But it will create the driver program locally on this machine, which would enable IntelliJ IDEA to debug this program. So now we can just simply debug this program by clicking debug button. And in the output, we'll be able to observe if our local driver is able to connect to the remote cluster. So we can see that it starts requesting application master container from the remote cluster. And now it's uploading resources for the job and already created Yarn application in the cluster and started executing of the job. And as part of the execution, it hit our breakpoint that we set directly in the cluster. Here we can do a variety of debugging steps. One of the interesting of which is to execute batch commands. For example, we can take few rows of the data directly from the RDD of this executing job. So I can expect on the fly what are the values of the variable in here to determine what to diagnose why my job may be executing incorrectly. And the wonderful thing here is that while in this breakpoint mode, Spark still will submit ad hoc jobs to the cluster and will actually allow me to, at runtime, to investigate my data, explore my data while I'm debugging my application. So now it executed this request and shows me that the first row of my data is actually a header, and that would give me a clue that why my why my application may have failed on this data set. So we can terminate that part, or actually let it continue, and switch back to our slide deck. So once you finish developing your application, the next step, logical step, is to achieve production deployment. And this is supported by a variety of services and tools in Azure. For batch pipelines, you can use Azure Data Factory to orchestrate your Spark jobs. And as part of the GA release, we'll actually enable highly availability for the Livy job submission service in the cluster. So that would be kind of ready for enterprise use. For streaming, for Spark streaming jobs, you can also use we can rely on Yarn deployment mode to achieve high availability of your Spark streaming jobs. And in terms of connectivity, you can connect your batch and streaming jobs to a variety of services in Azure, such as Event Hub, Power BI, and others. Recently, we released a Power BI connector, which you can find on this GitHub account. It's another open source project, which allows you to easily pump your data directly from your Spark streaming jobs into a real-time dashboard on Power BI. So in this talk, we discuss some of the benefits of Spark and variety of development tools and experiences that are available to you inside of Azure Cloud that make development on Spark productive. On this slide, we also provide some reference materials, such as Azure Spark documentation website that provide kind of further information about available services. Here is a link to our Spark Magic kernel, which is open source project, as well as Power BI connector. Thank you for your attention. Goodbye.